Hi, this week we are continuing with experiments on optics. This week we will do an experiment on image formation by lenses and mirrors. The study of image formation by lenses and mirrors is a very important aspect of optics. The successful operation of microscopes, telescopes, and cameras depends on selecting the proper optical components. The purpose of this experiment is to study the characteristics of mirrors and lenses and to learn how to apply the thin lens equation to several situations. When parallel rays of light hit the concave lens, it causes them to spread out from the principal focal point F. This is the reason the concave lens is called diverging lens. The convex lens takes parallel rays to a point and brings them together to a point F, which is a principal focal point, and this is why this lens is called a converging lens. You're seeing these concave and convex surfaces every day. For example, when you use a spoon, this side of the spoon is an example of concave surface, and the outside surface of the spoon is a perfect example of the convex surface. Focal length f is the distance from the surface of the lens to the principal focus point. The power of the lens is equal to the inverse focal length, and the center point of the lens, the point in the middle of the lens located on the principal axis, is called the optical center. And this axis here is called a principal axis. There are three principal rays for lenses. For this particular example, I am going to use these principal rays to create the image using the convex lens. And this is because during your experiment, you're going to use a convex lens and concave mirror. So as I said, there are three principal rays for the lenses. P ray is the ray that is projected parallel to the principal axis, and it will bend to pass through a focal point here, and this is a principal focal point. So our center of the lens is here, and then principal axis goes through center of the lens. The second ray is F ray. It's incident ray passing through a focus here, and then once it strikes the lens, it will bend parallel to the principal axis, like this. And the third ray is M ray that passes through the optical center of the lens and reflects back along the same path, like this. These three reflected rays will intercept at the same point, and this point here is the top of the image. Okay, so if we had object here, and this is the size of the object, and then we have real image here, you're noticing one thing: for the convex lenses, the image is real and is inverted. Before we talk about thin lens equation, let's talk a little bit about these distances here that we labeled on this figure. So O is the object distance from the center of the lens. I is a image distance from the center of the lens. F is a focal length for this lens. SI is the size of the image. And remember, in our case, image is inverted, so size of the image is going to be negative. And SO is the size of the object. Now, knowing these quantities, for example, if we know a object distance and image distance, we can calculate the focal length of this lens using a thin lens equation that states that 1 over O plus 1 over I is equal to 1 over F. Furthermore, we can calculate the magnification of this lens using this equation. It is a negative image distance divided by object distance, and it is also equal to the size of the image divided by size of the object. Now, sometimes, even during this experiment, you're going to use either that magnification is negative I over O, or the equation for magnification that states that magnification is equal SI over SO, and then you're going to get magnifications that are not exactly same. The reason for that, especially in your experiment, is because you are going to be able to more precisely measure the image distance and object distance, then you're going to be able to measure size of the image and size of the object. Knowing the magnification for your lens, you can tell if your image is upright or inverted. If the magnification of the lens is greater than 0, then you're going to have upright image. And then if the magnification of the lens is less than 0, then you're going to have inverted image, like in our example here. Now let's talk a little bit about mirrors. The reflection of light from mirrors may be treated by applying the law of reflection to each ray of light. When parallel rays of light reflect from the concave mirror, they pass through a focal point which is halfway between the surface of the mirror and the center of curvature of the mirror. The concave mirror is converging light to a focal point. For concave mirror, the focal point and the center of curvature are on the same side of the reflecting surface of the mirror. When parallel rays of light reflect from convex mirror, they diverge as they are originating from a focal point. For convex mirror, focal point and its center of curvature are behind the reflecting surface of the mirror. The focal length of the mirrors is equal to the 1/2 of the radius of the mirror, r in our case here, and it is positive for concave mirrors and it is negative for convex mirrors. A radius of the mirror is the distance from the mirror surface to the center of the curvature of the mirror, in our case C here. During the experiment, you're going to use a concave mirror. Now let's talk about principal rays and image formation for the concave mirror. So you have object here. The principal rays are same as the principal rays for the lenses. So P ray goes from the tip of the object parallel to the principal axis. Once they strike the surface of the mirror, they reflect back through a focal point, this way. The F ray goes from the tip of the object through a focal point of the mirror, and then once it hits the reflective surface of the mirror, it bends back parallel to a principal axis here. And then M ray goes through a center of curvature point here, straight to the mirror, and then it reflects back in the same way. Okay, so the point where all these three rays are intersecting, that is the point where the image is formed. And then same as for our example for the lens, the image here is going to be inverted. Same as for the lenses, you can use the thin lens equation. If you know the object distance and if you know the image distance, you can calculate the focal length of this mirror, and then the magnification of the image is given by this equation. It's negative I over O, and it's equal to the size of the image divided by size of the object, where here size of the image is negative because image is inverted. So if the magnification for this mirror is greater than 0, then you're going to have upright image. And then if the magnification for this mirror is less than 0, then you're going to have inverted image. The image distance is going to be greater than 0 for real image for the mirrors. And then the object distance is going to be also greater than 0 for real objects. Now let me ask you a question. If the light converges to a point after being reflected from a plane mirror, are the lights prior to striking the mirror going to converge or diverge? What do you think? Yes, you're right. If the light converges to a point after being reflected from a plane mirror, then because of the laws of reflection, the light rays prior to striking the mirror will converge as well. Remember that incident angle is going to be same to the reflecting angle. And this is called specular reflection. Okay, so now we are going to move on to a short demo on this experiment. So this is a setup for the experiment on lenses and mirrors, and this is a second week of the optics experiments. So you have this optical rail, optical bench rail, that has on this side this scale that goes from 0 to 1,000 millimeters. And then on the table across from you, this scale will go from 1,000 to 0. Just bear with it, you can calculate really easily the distances. Okay, so you have a light source, you have 3 component holders. On your table you also have a crossed arrow target, the viewing screen, you have a concave 25mm mirror, you have one convex lens that it has a labeled focal point on it, and then you have one convex lens that has unknown focal length. The goal of this experiment is to place cat crossed arrow target in one point, place the screen on another point, and then move the lens in between so you can observe either enlarged sharp image or reduced sharp image. And then by measuring the object distance and image distance and using a thin lens equation to calculate the focal length of these two lenses and the mirror. On your table, you're also going to have an information sheet where you have given offsets for the lenses and for the cat and the screen. Okay, so same like last week, this experiment is going to be done in dark. So before I turn the lights off, I'm going to place the crossed arrow target here close to the light source, and then on light source we also have this diffuser. So I'm going to place the crossed arrow target close to the light source. Notice that on these components holders there is this line here that indicates the position of this component holder on the optical bench. So let's say I'm gonna place it to a number that's easy to manipulate with at 20 millimeters. So now my position of the cat is going to be 20 millimeters minus the offset for the cat, and the offset for the cat is 4.5 millimeters. So the actual position of my object is going to be 20 minus 4.5 millimeters, and that's what? 15.5 millimeters. Then you're going to place, if you place all your optical components on the same side of this component holders, it's going to be really easy to account for offsets, because if you place them all on the left hand side left hand side you're going to subtract the offsets, and then if you place all of them on the right hand side you're going to add the offsets. Okay, so now I'm going to put my viewing screen at the distance that is the 5 times focal length of your known lens. Okay, so I'm gonna place this here, and then I will put my lens on the component holder and place it in between. Now I will turn off the lights so you can actually see the image formation. Okay, so now you see only a bright spot on the screen. If I move the lens closer to the viewing screen, you are going to see a image, and this is a reduced sharp image. And then if I move my lens away from the viewing screen, now you're going to see, this is much easier to see in dark on the camera, now you're going to see the enlarged image on the screen. Okay, so now let me turn off the lights again. In your laboratory manual, you are going to record a position of the component holder for the cat, for the lens, and for the viewing screen. Then you're going to account for the offsets, and then you're going to calculate the distance. This is O, it's the object distance from the lens to the object, and then the image distance is this distance from the screen to the lens. And then you're going to use a thin lens equation and calculate the focal length of this lens. And then same for the reduced image. Again, record. So the only position for the reduced image, only position of the lens changed. Again, record the raw values and then account for the offsets, calculate O, calculate I, and then use the thin lens equation to calculate the focal length of this lens. For the second part of the experiment, I'm not going to turn off the lights. You're going to use unknown lens, and then you will place the screen at a distance from the cat that your TA assigned to you. And then again, you're going to move this lens closer to the cat to observe enlarged sharp image, and then closer to the screen to observe a reduced sharp image. And then again, repeat the same procedure, measure O, measure I, and then use thin lens equation to find the focal length of this lens. If you are careful with calculating offsets and reading the raw positions, you're going to get your results within 2% to 5% error. One direction, and then arrow of the image points in other direction. That's because for the convex lens, you're getting the real inverted image. So when you're calculating magnification using the image size and the object size, your image size is going to be negative because it will be virtually below the principal axis that goes through the center of this lens. The size of the object, let's say diameter of this, outer diameter of this circle on the cat is 1 centimeter. So then you can measure the size of the image on the viewing screen, on the scale on the viewing screen. Okay, so now let's set up for the mirror. You're going to replace the lens with the mirror. Now, you know when you look yourself at the mirror, the image is not going to be behind the mirror. You will observe image here. So we're going to take the screen. Notice that on the screen you have these strips. So put the screen here, not blocking the cat completely. So this strip is on the vertical because the screen is translucent. Okay, and now move the mirror to the point where you see the sharp image. You see here, this second part, this is your image. The first, what you see on this side, that's your cat, and this is your image. So you're gonna move the mirror. You see, as I come in closer, I'm seeing the sharp image. Okay, so now you're going to again, let me turn off the lights again. So now you're going to record the position of this component holder. And this one component holder has cat, that's your object, and the screen, which is the image, and then the raw position for the mirror. So to find the position of the mirror, just subtract the offset for the mirror here, and then the position of the object didn't change from before because you didn't move this, right? So it's going to be a raw position minus this one, but the position of the image is going to be a raw position plus offset for the screen. You need to remember all of these lenses are same, so the offset for unknown lens is the same as the offset that's given for the lenses on the on your information sheet, and that offset is 6.5 millimeters. So once you calculated the positions with the offsets, you're going to calculate the object distance, image distance, and then use the thin lens equation to calculate the focal length of this mirror. Once you're done with the experiment, you're going to turn the light source off, take all these optical components and place them on the rail like this, and leave the station in exactly the same condition you found it when you walked into the lab. This is all for this week. Thank you.